I'm a new research fellow joining CCM this summer. So today I will talk about symmetry preserving neural networks. So the goal of my talk is to show you a specific mathematical problems, approximation problem related to the symmetries in our 3D world, and show you one way to preserve those kind of symmetries with neural networks if you want to do some kind of supervised learning problems with your data. Okay, so symmetry is important and ubiquitous properties in our physics. So before I show you the mathematical formulation of the problems we are considering, let me first provide you two examples that motivate me to consider the symmetries. The first problem is potential energy in molecular dynamics simulations. So thanks to some yesterday talk, so I can simplify the background a little bit. So the potential energy is the key center point we need for simulate molecular dynamics. Say we are interested in the potential energy of a small systems consisting of a single item, say Cooper. Okay, so the only information that determines potential energy is the coordinates of n atoms, x1 to xn. So if we want to get the potential energy accurately, we would like to solve the quantum mechanics, the Schrodinger equation, to get the ground state energy. Then we get the potential energy to simulate dynamics. But in order to get those kind of chemical accuracy, if n is large, the DFT computation or other computation methods are very expensive. So we would like to have some approximate potential energy function that has the same accuracy or similar accuracy as the Schrodinger, the quantum mechanics methods, but much less computation complexity. So in that sense, we want to fit an energy function which takes all the coordinates x1 to xn as the input and get output as the potential energy. So this is a purely supervised learning problem. You can interpret it like that. You collect enough data a priori, generated from expensive computations, and hopefully, if your machine learning model, either regression, kernel method, or neural networks, are expressed enough to get a good model, then when you want to evaluate the potential energy during the simulations, you do not need to call any quantum mechanics solvers. You can call this machine learning model directly to get much faster simulations. Okay, but we know this potential function we are interested in has certain symmetries, and we would like to preserve those kind of symmetries when we fit this function in our machine learning pipelines. So what kind of symmetries we are interested in? First is the translation symmetry. So this is very straightforward. If you translate all the coordinates in the same directions, they should provide you the same potential energy. And the second is the rotation symmetry. Okay, this is another way saying the potential energy is independent of the frame. If you rotate your lab frame with the same rotation matrix R, it should return you the same potential energy. And the third symmetry is called the permutation symmetry. So this is a different concept, saying because our potential energy should be indifferent with the index of all the atoms of our consideration. So say you have a permutation representation sigma, okay, on the set 1 from n. If you apply any permutation on the index, it just still should return you the same potential energy. So those three symmetries are the main symmetries we are interested in this example. Okay. And the second problem I'm saying here is about PDE solving. Say we have a very classic transport diffusion PDE. So the C is certain concentration of our interest. The first term is diffusion term. The second term is the convection term, and you have source term S. It may depend on it is a nonlinear function, so the whole PD is nonlinear. Okay, so from a traditional PD solving viewpoint, okay, you can apply certain spatial discretization. Say you have a discretization of a domain x1 to xn, and say you know the velocity field u. Okay, the unknown function is c, of course. You also get the discretized velocity field at those at those grids u1 to un. Okay, then presumably if you call any PD solver with this fixed grid, you can solve out the solution C at those grids. Okay, so implicitly this PD defines your mapping from x1 to xn and u1 and un to your solution C1 and Cn. Okay, and then say if you are interested in certain quantity I. Okay, so here I just make up one. Okay, the integration of your solution C over the whole omega. Okay, so this I is a solution, is a function of C. So essentially it's a function of x1 to xn and u1 to un up to your spatial discretization. So this is a well-defined mapping. So in traditional PD solving, okay, you would probably not think about it in this way. You are just interested in solving the PD and get this quantity. Okay, this is totally fine. But if you have certain uncertainty in your PDs, say you do not know the information of S. Okay, so you want to do some inverse problems. So one way to do is that, okay, you solve this inverse problems S, and then you can again call your forward formulation to get this quantity. Okay, so now from perspective of machine learning, we want to do it in an end-to-end way. Okay, so suppose without knowledge of S, but we can collect certain information as supervised learning data pairs. The input is x1 to xn and u1 to un, and output is the integral in quantity I. Okay, and you want to find a mapping from those inputs to the quantities directly without solving the specific S. Maybe you are not so comfortable with this form, with the exhibitor form. You are interested in this quantity. Okay, so again, you can imagine now this function I has the similar symmetries as I shown in the previous slides. It has at least three symmetries. Again, first is translation. Okay, if you translate the whole domain, the solution is the same and the quantity is the same. If you rotate your laboratory frame, it gives you the same quantity. And again, this is integral quantity is indifferent with your index of the spatial grids. So if you permutate over the index simultaneously with x and u, you should get the same quantity I. Okay, so you can see both the potential functions E and the quantities I here possess the same symmetries. Okay, so now here is a simplest problem set of these kind of functions. Okay, say we have a scalar function f maps a set of coordinates. Okay, so this is like the potential the market dynamics example. We only have the x information, no u information. Okay, and the f maps these coordinates to output y. Okay, and we can of course have certain data determined by this mapping, and now we want to do it. We want to fix a function in a supervised learning way. Okay, find the functional form, fitting this function, fitting this data, and preserve all the symmetries simultaneously. All the three symmetries I mentioned simultaneously. Okay, so this is the mathematical problems I'm proposing right now. So before we provide one answer to these problems, so first, why we would like to preserve the symmetries if we do supervised learning in such a way. So okay, conceptually, of course, it preserves and respects the physics. Okay, we should expect it is a nice thing. Okay, without violating the physics. But to be more practically, okay, two important reasons we want to preserve symmetry is for the purpose of better data efficiency and better accuracy. Okay, why would I say so? So for data efficiency, you can say, okay, if I have two input data, x x1 to xn and x1 prime to xn prime, they are equivalent up to translation or rotation. So essentially, they are same set of data because output of y are exactly the same. But if you do not preserve symmetries, they are different to machine learning models. And if your machine learning models preserve those kind of symmetries, so you can simultaneously learn the data up to arbitrary equivalence of translation, rotation, and permutation. So in this sense, preserving symmetries can provide you better data efficiencies. And following a similar argument, you can imagine this kind of thing. Preserving symmetries can also provide you better accuracy, especially in the generalization regime. Okay, if you learn certain configuration of x1 to xn accurately, then up to rotation and the translation and permutation, they are always within the same accuracy. So this is another perspective to think about symmetry preserving. Okay, so one thing I want to clarify is that this argument does not hold from our traditional way of PD solving or quantum mechanics. When you think about that, when you solve Schrodinger equation to find the ground state or find traditionally solving the PDE, you do not care about symmetry preserving so much. Okay, your solution may change a little bit if you change your rotation frame, but in that sense, that doesn't matter because you are applying certain algorithms up to certain accuracy guarantee. Since the true solutions is invariant, so as long as you have those kind of accuracy, as long as your algorithm has certain accuracy, it's fine if you do not preserve the symmetries. But in the pipeline of machine learning, you a priori have certain data set and you want to learn the function from that data set. So you want to extract as much information as possible from that data set. So that's why, from machine learning perspective, we are particularly interested in this kind of symmetry preserving properties. Okay. So of course you can imagine this is a very fundamental questions. It appears in a lot of physical situations, and of course there are a lot of related work. So here is just incomplete list. So the first thing, a line of work are mostly related with potential energy functions. So I think that's perhaps the one of the most important problems that in scientific computing attracts those kind of thinking. So traditionally, people will handpicking certain features that are invariant under those group operations. So as long as you have some features that are invariant under translation, rotation, and permutation, then you can apply any machine learning model you like. The output should also preserve those kind of symmetries. So like Gaussian approximation, potentials, smooth overlapping of atomic positions, those kind of thing. And then one important work is called BP neural network. So it is in the same spirit of the handcraft features, but introduce neural networks to replace the kernel method, and it achieves the state of art at that moment. And what we are proposing right now is essentially replacing those handcrafted features with some learned features. So this kind of new thing is very similar to what happens for computer visions. Priori, people use some hand-picked filters, and now with convolutional networks, people parameterize with those filters and learn it from the data. So our work are thinking in a similar way. We want to learn those kind of invariant features from the data end to end, and then apply certain fitting model to get to the final output. So there are a lot of neural networks thinking in this line. And another line of research addressing the similar problems is called is based on certain group representation theorem. Because you can decompose, especially the rotations group in either 2D or 3D cases with certain representation, and then with the representation, you introduce certain non-linearity to guarantee the approximation, to guarantee the expressiveness and the symmetry preserving properties. So like group equivariant convolution networks, steerable convolution networks, Clevish-Gordon nets. When I look at the FWAM conference, I realized that last year, Risi gave a nice talk on equivariant networks. So,
could you tell us a little bit, what is your data? Like, do you need DFT trajectories of all the atoms of your system?
Yes,
how do you train?
Yes, so we need the data generated from in DFT in the context of molecular dynamics, or we need data from PD solvers in the context of the second example. So the data essentially are the one pair of data is a set of coordinates x1 to xn and output y. Mm-hmm. So that's called one pair of data. And, sorry?
In advance.
Yes, we assume the data intrinsically carry out the three symmetries I mentioned earlier. Okay. Oh yeah, I just mentioned that Risi gave a nice talk on the last line of research. Okay. So what's our way to preserve all these symmetries with neural networks? So let's see. So remember that one important goal of our neural network is to preserve all three symmetries simultaneously. Okay. So if you were only interested in one or two symmetries, it's relatively simple. Okay. So let's first start with that point. Okay. The translation symmetry obviously is the simplest way. Is the simplest one to guarantee, because you can use relative coordinates. Then your input information would always be invariant under translation. So for example, you can compute a certain center of your coordinates denoted by x bar. Then you instead of using x1 to xn, you use x1 minus x bar, xn minus x bar. This information is already translation invariant. Okay, so this is simple to achieve. Okay, then next, what is rotation invariance? Okay, so one way to get rid of the dependence of rotation is to compute the pairwise inner product between x1 prime and xj prime, which we define here, that are already translational invariant. Okay, then you get inner product matrix Dij. Actually, D prime is of size n by n. Okay, so mathematically you can prove D is a complete information of the coordinate information up to rotation. So once you get the the matrix D prime, you can recover the coordinates x1 to xn up to rotation. Okay, so D prime carries out all the information, but there's one thing we should point out, that the matrix D does not have permutation invariance. So you remember the D matrix is of size n by n. So it depends on the index of your coordinates x1 to xn. If you permute the index, the columns and the rows will also permute. Okay, so we want to fix the permutation invariance. We want to fix the permutation invariance in this kind of thing. So what's the way to do that? So we will first look at what's the general way to fix the permutation invariance. So that's one paper called deep sets. Sorry, I did not put the reference here. You can search it. You can Google it easily. So it proves that actually, if a function, suppose we have function f, okay, operating on a set x1 to xn, okay, we say a function operating on a set, meaning that the function f is permutation invariance. Okay, so if it is a function operating on the set, then the function f must can be represented in such a way. Okay, so it consists of two functions, rho and phi. So phi is a function acting on each element of this set x1, and then you can think it is like a feature extraction. Then you always sum over all the extracted features phi, and then put that to another unknown function rho to get our final output. So this is similar to the Kolmogorov-Arnold representation theorem in general functions. But here, since we know f is permutation invariant, so the inner functions phi is also is shared around all the comments. So you can see, since here I is the dummy index, if you sum over I, the final functions must be permutational invariant. And so this is the mathematical theorem of the permutation invariant functions. Okay, to give you a quick example. Okay, so here if we have two scalar input z1, z2, these functions are permutation invariant, and you can easily find that this function can be written in this way. So if I define this phi as the z and the z square terms, and the rho as square terms and b, so these invariant functions can be written this way. So it's basically a symmetrization of symmetric polynomials, and you can be convinced this is true for general symmetric polynomials with n elements, and then it also holds true for general functions if you can apply this polynomial approximation. Okay, and so the idea of deep set is that given this kind of general representation, we just parameterize these unknown functions phi and rho with neural networks. Okay, keep in mind that the key for this representation formula is that this phi can be multi-dimensional functions, just in the same spirit of Kolmogorov-Arnold representation. So first, you're lifting the input xi to certain feature space, and then you always average them and get or sum over them and get the final output. Okay, so this is the way to guarantee permutation. Okay, and then now we can compare all the techniques together to get our solution to get this neural network. So this is the most important slide of my talk. So we first introduce a set of M embedding functions that embed each taking the magnitudes of xi prime as input, and then provide an average of all the x. Okay, so here J is the spatial index from 1 to 3, and the K is the index of embedding functions. So from 1 to M is the number of features you select a priori. So if you write it in the matrix form, this L is G QTA times G transpose times the input matrix X, where G is a weight matrix or embedded matrix that are invariant to both translations and the rotations. Remember, xi prime are already translational invariant, and we only take the magnitudes. So each element of G are translational and rotational invariant. And since we take the average, then the final output L are also permutational invariant. And then, L is permutation invariant, but L itself is still not rotation invariant because it depends on X. Now we compute the inner matrix, the inner product between L and L transpose to get this matrix D. Then you can easily prove the D preserve all the symmetries. Okay, so it's like you first compute the inner product of X transpose and X, and then project to those spaces you predefined, and sum it, average it together to get those symmetry preserving feature matrix. And next step is very simple. You just take a D as a vector and put it to another fitting function rho, and final output will also preserve all the symmetries. And we propose to parameterize FWAM and row within networks. Okay, so this is the way we preserve the symmetries, and there are a lot of extensions for in this line. For example, you can guarantee certain equivariance if your output is not just scalar but a vector. Okay, then you have those kind of equivariance. If your output is a tensor Q, you can also ask for those kind of equivariance. So those kind of things can also be achieved following the same idea. You just trick a little bit on the final output. And you can also guarantee invariance and equivariance if we have some additional scalar, vector, or tensor features attached to each point. If you, like in the second example, if your input is not only x but also u, you can also ask for those kind of symmetries. It's also possible to achieve. And the further thing is that, so here, when we do embedding, we only use the information of xi prime, a magnitude of xi prime. So this is like the zeroth order information. So it is not universal approximation. If you want to make your model more expressive, you can use some higher order information to do embedding. Okay, this is also possible. So this long research is still ongoing. I think one big open question is that, okay, can we find some ansatz that has universal approximation property with practical optimality and scalability? Okay. Okay, so I think I have run out of time, so I will skip off the application results on molecular dynamics and those PDs. So here one figure is showing that, okay, this is evidence showing that if we impose the permutation symmetry as shown on the red line, the data efficiency or the accuracy can be much better than the blue line without a permutation symmetry. Okay. Yeah, I think I will skip over the results and happy to take questions. Thank you.
Okay, we're a little bit over time, so maybe take one question if there is any. Otherwise, we go on. One question?
One question there?
No?
So you didn't say too much about, I mean, I didn't have a good way to internalize the computational complexity of these models. Can you say, I mean, a little bit more about what scalability and those things look like?
Yes, okay. That's a good question. So the computation complexity, okay, depends on a few things. First, the number of features you choose. This is m. Okay, and in terms of complexity n, then this is linear with n. So if you are considering a small graph, this is fine. But if you want to push, I didn't mention that if you want to apply it in molecular dynamics, you will encounter million atoms. So in that case, we like to leverage the locality of the functions. So we can divide a large point clouds into a lot of small counterparts due to the short range effect of the force field. Then you can think the whole complexity is the number of point clouds of overall number of clouds times the locality of your point clouds.